Okay, good evening all. You can mark your attendance. Google form is available in your class group. You can mark your attendance. So yesterday we were talking about the cascode amplifier and its different versions. So till now we have discussed about the double cascoding and folded cascode. Okay, these two are the two different versions of cascode amplifier. And the advantage is that it has more output resistance, isn't it? Double cascoding means we are stacking one more transistor so that the output resistance will increase. So that is very much desirable for a cascode amplifier is concerned. Again, folded cascode, we will be able to make use of PMOS and NMOS together. But the drawback is that we require two separate current sources for that. Okay. So that is what we have discussed yesterday. So this was a circuit of folded cascode. We make use of two transistors, PMOS and NMOS together. And the advantage is that it will also increase output resistance, but drawback is increased chip area, and we are using two separate current sources, one for PMOS and the other one for NMOS. Okay, separately we have to use I1 and I2. Whereas in the previous version we will be making use of only one current source which is common to both the transistor circuits. Okay, but the advantage is that we are exploiting the use of both transistors together, and at the same time the complexity, that is the power dissipation, is very less because we are making use of only one transistor under one power supply. Okay, whereas in the previous version we are doing, see, three transistors together, it is being stacked under one power supply rate. So this is very difficult to manage. Excessive power dissipation will taking place across a transistor, so that will increase your heat dissipation as well. So it will affect your IC, okay, and it will affect the age of or life of the IC as well. But in the folded cascode, by using this arrangement, we will be able to make use of both the transistors PMOS and NMOS, and simultaneously the chances of power dissipation and getting heated up can be avoided. But the disadvantages, we are using two separate current sources, that is one for Q1 as well as the another for Q2. So that is a disadvantage. Now coming to the next configuration of cascode amplifier, that is bi CMOS. So from the name itself, it is obvious that here we are making use of both BJTs as well as CMOS together. Okay, bi means bipolar, CMOS means complementary MOSFET. So together we are simultaneously using in the same circuit both BJT as well as CMOS. And the advantage is that, so you can read this particular sentence here. The bipolar transistor is used for cascode device that's provide a large output resistance than it is possible with a MOSFET. So normally you will be using two MOSFETs, isn't it? So in the cascode device, we'll be replacing this MOSFET with BJT. Understood? So in bi CMOS, what we are doing is, normally the second stage it will be CMOS, but now we are trying to replace this CMOS with BJT, which is offering better output resistance because beta value will be larger, isn't it? Otherwise it will be A0 into R0. You know the output resistance of common gate, it is A0 into R0, but when we replace this MOSFET with BJT, now the output resistance has become beta times of R0. And consider that the value of beta of a transistor, typical BJT, is very much greater than that of MOSFET. Okay, you know that the MOSFET's gain is represented by A0, the MOSFET's intrinsic gain is represented by A0, but here you have transistor, that is BJT, whose current gain is represented by beta. The value of beta is very much larger than that of A0. So in effect, what is the conclusion is, this transistor, when it is replaced on the place of MOSFET, it is offering better output resistance or larger output resistance, which is always desirable for a cascode amplifier. Understood? So that is one benefit. Second benefit is the bipolar transistor provides lower input resistance. Okay, it is offering higher in output resistance and lower input resistance. See here, its input resistance being lower means this, it is connected to the output of first stage, isn't it? This thing Q2 is a bipolar transistor or BJT, which is being connected in a common base configuration. This is in common source configuration. So this common base configuration BJT is connected to the output of common source. So it is offering lower input resistance, means the overall resistance at the drain of Q1 will be lower. Okay, So the result is lower total resistance between the drain of Q1 and the ground, and hence a reduced Miller effect. So this is another second advantage of this configuration, that is reduced Miller effect. What will happen if Miller effect is very less? If Miller effect is very less means it will offer better frequency response, or in the high frequency also the gain will be predominant. Normally at high frequencies what will happen for the gain of the amplifier? It will start decreasing, isn't it? So that doesn't takes place here because of high frequency, or because of better high frequency response. Okay, the performance of high frequency is very much dominant here because of high gain. The high gain will be prolonged over high frequencies. Okay, it doesn't decrease. The gain will not decrease in high frequency because of this reduced Miller effect. Due to Miller effect only, at high frequencies we are experiencing less gain, but that doesn't take place in this particular BiCMOS configuration. That is second advantage. So I'll repeat once more. In BiCMOS, what you are planning is you are connecting the two configurations together. One is BJT, the second one is CMOS. The lower part is MOSFET, the upper part is bipolar. So together it is known as BiCMOS. The lower part is common source. You know, the it is common source because source is common for both input and output. Vi is your input and output is taken at the drain. This output is connected to Q2. So Q2, to the emitter you are taking input, and from the collector you are taking the output. So it is common base. So Q2 is common base configuration and Q1 is common source configuration. So this common source and common base together they act as BiCMOS, and the advantage is that first advantage, it is offering very high output resistance because as indicated in the figure, the output resistance is beta R0. Normally, for a cascode version, it will be, for a normal cascode version, it is A0 into R0, isn't it? So instead of A0 into R0, here it is beta into R0. See, beta into R0. So A0 has been replaced by beta. Beta is the gain of current gain of transistor. It is very large. It is very large when compared to A0. So a large output resistance is offered by this particular transistor means that is better for our cascode amplifier. Always a large output resistance will get you better gain. Okay, so gain can be increased only if it is possible to, increase high output resistance. So that can be achieved by using a common base configuration that is being stacked over common source. Okay, that is the advantage of using BiCMOS. The second advantage is that it will reduce the Miller effect because the second transistor, which is acting as a common base configuration, that is offering less input resistance. Okay, so less input resistance means actually that input is connected to which circuit? See, this input is connected to which circuit? It is connected to drain of Q1. So since the common base transistor, that is Q2, it is offering less input resistance to Q1, I can say that the output resistance of Q1, because output of Q1 is same as that of input of Q2, isn't it? So the output of Q1 is nothing but the drain. So the drain resistance of Q1 with respect to ground will be lower, and hence it will reduce the Miller effect. Okay, so due to the reduced Miller effect, the high frequency gain will be substantially high. Means in a normal amplifier we are expecting low gain at high frequency, but that will not happen here because it has reduced Miller effect. Okay, the Miller effect has been considerably reduced because of the use of this BiCMOS configuration, and we are expecting a stable gain at low to high frequencies, which means that you can enhance your bandwidth. Okay, so you will get high bandwidth in this particular configuration. And later what I will do is I will be replacing this particular circuit in a next some modification. Okay, so that is being shown in the second circuit, that is figure number 11b. So what is the difference between the previous and the present circuit? What is the difference? In the previous circuit, Q1 was MOSFET. Now here Q1 is BJT. Okay, and apart from that, in the earlier circuit I have used one MOSFET and one BJT, but here I am using two BJT. So one more BJT I have stacked over Q1. So Q2 is being stacked over Q1 so that it will increase the output resistance. Okay, so the purpose of stacking an additional transistor over Q1 is to achieve a better output resistance. So by arranging in this manner, that is initially BJT, again BJT, then after finally MOSFET. So by arranging in this manner, you will be able to produce better output resistance when compared to the previous case. In the previous version, I am having only an output resistance of beta times of R0, but in this version, I'm still increasing. I'm trying to still increasing the output resistance by stacking one more transistor in between, that is nothing but Q2. Okay, so Q1 is having R01. See, as mentioned in this particular circuit diagram, the transistor Q1 is offering a output resistance of R01. So meanwhile, if you connect Q2 over this Q1, it will increase the output resistance by beta times, that is beta 2 into R02. Okay, so this will be the output resistance of Q2. Again, if you stack the CMOS is in CG configuration. Okay, CG, these two are in common emitter configuration. Okay, so once you stack the CG, it will multiply this output resistance by A03. Okay, so A03 is the gain of Q3. A03 is the gain of the MOSFET Q3. So the overall transistor gain becomes, overall circuit's gain will become A03 into R beta 2 into R02. Okay, so by stacking in this manner, we'll be able to get better output resistance. You know what is the advantage of getting better output resistance? Because larger the output resistance, larger will be the gain of the cascode amplifier. So that is a conclusion. That is how we can design a cascode amplifier in which configuration, in BiCMOS configuration. All these are different versions of cascode. Okay. Till now we have studied a typical cascode amplifier, followed by the double cascode, then folded cascode, again BiCMOS cascode. So all these are different versions of cascode amplifier. So that completes the first part of this particular module. So whatever we have studied, we can just go through it. See, first topic we have discussed about the small signal analysis, where we have derived some sort of parameters of a cascode amplifier like gain, that is open circuit voltage gain, overall voltage gain, input resistance, output resistance, everything we have derived. Secondly, we have analyzed the frequency response of the cascode amplifier. There we find the expressions for cutoff frequency, FH, and we compare that result with respect to the ordinary CS amplifier. That is, even though you are getting a high gain in cascode amplifier, but we have to compensate in the cutoff frequency or bandwidth. Means whatever, how much times you increase the gain. For example, you increase 3 times gain, means you have to compensate in the bandwidth by 1 by third. That is 1 by third. The bandwidth will reduce by 1 by third, reduce to 1 by third. Okay, so whatever the gain you have achieved, the same factor you are compensating in the bandwidth. That is the result of frequency response, what we have learned. Next thing we have discussed about the typical cascode current source, where that cascode version is able to produce a considerable or desirable current at a particular location. Next three are the different versions of cascode amplifier, like double cascoding, folded cascoding, and BiCMOS cascode, in which each of the circuit are able to provide better output resistance. So here high output resistance can be provided by the BiCMOS configuration, which is able to exploit the advantages of both BJT as well as CMOS together. Now the second part of this module, here we will be discussing about the different current mirror and current source circuits. You know what is a peculiarity of a current mirror circuit, right? That is, in an IC we will be using different uh, discrete components. Okay, certain components will be operating in one current, the other components will be having saturation of another current. So need not necessary that all those particular circuits should given separate current. So that will be complicated, it will increase the hardware complexity of the IC, and it is very difficult to fabricate also. So what you will do is, considering one location of an IC, you will be producing a current for that and steering this current to all other locations of IC. That is what is the benefit or the advantage or use of this current mirror. So current mirror is a particular circuit which is used to steer the current from one part of the location or one location of the IC to all other connections of IC, all other connection points of ICs. Okay, in certain cases, all the components will have same current. So a perfect mirror circuit is required, because in perfect mirror circuit, you are always expecting a current transfer ratio 1:1. You know what is current transfer ratio? It is I0 by IRF. You have studied in third module. If I0 is equal to IRF, means you have developed same output current as that of the reference current. Okay, but in certain situations you won't be able to, or you want some other current of other magnitude. So in that cases, what you will do is, you will have to produce current sources. Okay, that is not a current mirror, that is current source. Got the difference between current mirror and current source? No, in current mirror I0 is equal to IRF, but in current sources we will be producing I0 which will be different from IRF. or they will be having a mutual relationship, maybe 2 by third of IRF or 1 by half or 1 by 2 of IRF, like that. Okay, so there is a definite relationship between I naught and IRF in the current source circuit, but as far as a current mirror circuit is concerned, always you have a 1:1 ratio between I naught and IRF. Okay, so all those different versions of current mirror circuits are going to be discussed in the second half of this module. So this is going to be very important. So if you have any doubt, you can unmute and ask me. Don't hesitate to ask doubts. Okay. Feel free to ask any kinds of doubts. I'll be able to clear. So first is cascode MOS mirror. So let us look how this cascode MOS mirror works. So from the name itself, we are cascoding one stage over another stage. Cascoding means using different configurations together. It is not cascade. Cascade means it is similar configurations together. Cascode means different configurations together. Okay. So in a normal MOSFET mirror, what you have learned in third module, you're having only two transistors. Remember, no? Conventional mirror circuits, what you have learned in third module, it is having only two transistors or two MOSFETs, Q1 and Q2, which are connecting in a peculiar manner. Okay, so that is able to produce a definite amount of current from the reference source. Okay, there will be a reference current. So based upon that reference current, it will be able to produce a particular amount of output current, maybe half or 1 by third or 2 by third, or perhaps I naught will be equal to IRF. That depends upon the perfection of the mirror. Okay, so if you're taking the two transistors similar, means the W by L ratio same, aspect ratio same, means you will be able to achieve I naught equal to IRF. Understood? So that is in the designer's hands. The designer wants to have a particular amount of I naught, he can connect as such. Understood? So designer will be able to produce any desired amount of I0 depending on the value of reference current and other circuit parameters. Fine. So here cascode MOS mirror means when you compare with a simple MOS mirror, here we are going to cascode one more stage over the previous stage. So stacking one more stage over the conventional simple MOS mirror that is being exploited in cascode MOS mirror. Understood? In normal MOS mirror, you will have one stage, but in cascode MOS mirror, you will be replaced or you will be stacking one more stage over the previous stage. Okay. And the advantage is that it will offer better output resistance. Why you want better output resistance? Because here it is used in cascode amplifier. The same current mirror circuit we are using in the amplifier, because you know when you consider the amplifier circuit, you are always using a mirror there, isn't it? So that mirror circuit we have to design. So that design should ensure an output resistance which should be equal to the out load resistance. Okay, the load resistance of a cascode amplifier should be very large in order to provide high gain. So that load resistance should match with the output resistance of a mirror circuit. So while designing any mirror circuit for a cascode amplifier, we should be able to get a very high output resistance. For that only we are stacking one stage over the other. Understood why we are stacking one stage over the other? Because stacking one stage over the other will produce better output resistance. Because in a cascode amplifier we are trying to increase the output resistance, because increasing the output resistance will only increase your gain. Okay, so that the output resistance of this cascode amplifier should exactly match with the load resistance of the amplifier, then only proper biasing will occur. So this is the circuit diagram of a cascode MOS mirror. See, the simple version of this MOS mirror you have already learned. Actually, in the simple MOS mirror, you are having only Q1 and Q2, and this I reference will be here. Understood? This part you have learned actually in the third module. This is a simple MOS mirror where this I reference will be at the drain of, this will be at the drain of where? At the drain of Q1. Okay. Apart from this Q1 and Q2 and I reference, I have stacked two more transistors Q3 and Q4 in a similar way. Whatever the circuit arrangement, it is shown in the lower portion. Same replica I have connected to the upper portion also. Okay. So thereby we are stacking common gate over common source. Understood? So which is common gate here? Which is common gate here? Is it Q3 or Q2? Which is common gate here? Anybody? Which is common gate here? Is it Q3 or Q2? No response. Which is common gate here? Common gate means gate should be common to both input and output. So here it is, output is taken from drain, input is taken at the source. So here it is common, isn't it? Common gate is common to both the input and output side. So Q3 is acting as CG. Meanwhile, Q2 here, see, input is at gate, output is taken from drain, because this output is connected as input here. So this is common source. So Q2 is common source, whereas Q3 is common gate. So we are stacking one more pair at the upper end so that it will produce a better output resistance. Okay. So this is the circuit configuration. Now I will be trying to express the output resistance of this particular mirror circuit. So this is actually a perfect mirror circuit. Mirror means I naught equal to I reference. Okay. So whatever you are producing here, whatever I naught you are producing at this particular output, that current will be same as that of the reference current. Okay. Suppose the current I0 is flowing across Q3. This I0 will be equal to I reference for a perfect mirror, provided all the transistors are matching transistors. Matching means they should have same or identical aspect ratio, and all other parameters there, it should be same. So if you are able to take all the transistors Q1, Q2, Q3 and Q4 alike or identical or matched, then you will be able to get output current same as that of the reference current. So I0 is equal to I reference. So whenever I0 is equal to I reference means your current transfer ratio is 1:1, which means this is a perfect mirror. But for that you have to maintain a very high output resistance. So I am trying to find the output resistance of this particular mirror circuit. So for that we'll be starting with this particular equation. R out is equal to R0 plus 1 plus GM plus GMP into R0 whole multiplied by RS. So this is the actual output resistance of a cascode amplifier. Okay, this is the output resistance of a cascode amplifier which we have derived in the previous derivation, that is in the small signal analysis we have derived this particular equation. So consider what is R0 here. R0 is the output resistance of third stage, that is Q3. Okay, Q3 here output can be represented as R03. So here R0 can be written as R03, then GM is GM3. So all things it is relevant, it is with respect to Q3 only, because Q3 is the output. Understood? When you observe the previous circuit of the current mirror, that is cascode MOS mirror, it is obvious that you are taking the output from Q3. So this particular equation, even though it is a general equation for a cascode amplifier, this is a general equation for a cascode amplifier, but that we can apply to the mirror circuit by replacing appropriate subscripts. Okay. So here R0 can now be replaced by R03 because we are writing the output resistance with respect to Q3. So R0 can be written as R03, GM can be written as GM3, GMB can be represented as GMB3. Okay. And what about RS? RS is a source resistance. See, when you go to the circuit diagram, you will observe that the source of Q3 is connected to output of Q2, isn't it? So output of Q2 can be represented as R02. I repeat, the source of Q3 is connected to output of Q2. So output of Q2 is represented as R02. Therefore, as of now, I can write RS as, you can write RS as R02. Understood why I have written RS as R02? Because the source of Q3 is connected to drain of or the output of Q2. Output of Q2's resistance is R02. Therefore, source resistance is R02. Now replace all these parameters in this equation. It will be like this. Understood? Now open the brackets. So equation will be like this. When you open the bracket, it will go like this. And you know that the value of transconductance is very high. So whenever you find any term where you have a transconductance, that can be retained there. At the same time, it will be very large when compared to the resistance terms. Okay, the resistance to output resistance of a typical transistor is very much less when compared to the conductance. So whenever you have any term multiplied by a conductance, it will be large so that the other parameters can be neglected. So I have neglected this R03 and R02. At the same time, GMB3 it is nothing but the body effect, the transconductance due to body effect. You know the expressions of GMB is chi into GM, which you have learned in second module. Okay, that is body effect. The conductance due to body effect is equal to chi multiplied by the normal transconductance. So Instead of GMB3, I put chi into GM3, and the common factor is GM3, R03, R02. When you observe these two equations, GM3, R03, R02 is common. Take it outside. So in the remaining, inside the bracket, you are having 1 plus chi. And you know the value of chi is approximately 0.1, 0.2, which is very much closer to 0. So it can be neglected. So I considered that the value of chi is very much closer to 0. So I have neglected it. So the overall output resistance now approximately it is equal to GM3 R03 R0. Okay. So what is GM3 R03? Can anybody tell what is GM3 R03? See, try to respond. Then only I will be able to ensure that you people are listening or learning something. What is GM3 R03? What is GM3 R03? GM3 is a transconductance, R03 is the output resistance. So when you multiply that, what you will get? GM into RD is the gain. GM into output resistance is always gain. GM is the transconductance, output resistance is the resistance with respect to the output terminal of the MOSFET. So when you multiply the transconductance and output resistance, you will get the gain. Which gain? Gain with respect to Q3. Okay, so that is A03 only. So A03 into R02, that is nothing but your R0. I don't know whether you are studying or not. Please try to understand, all these are very easy only, but the thing is that you will have to practice. You have to practice and you have to study. Otherwise, it is very difficult to score marks in this paper. Okay, please keep it in mind. You have to practice this. Listen to the class. Most of them are skipping the class. I don't know whether they will be able to write the SE examination properly or not. Okay, so keep always give priority to this paper. It is going to be difficult for you unless you study. So practice all the derivations. Try to listen to the class. Try to understand the concepts. Then only you will be able to produce the papers. So this is the overall output resistance of this configuration, which is nothing but gain into R02. Okay, so that we have analyzed. So a typical cascode MOS mirror. So till now we have learned the cascode MOS mirror, where we have stacked one more stage to the previous stage, which is able to produce a large output resistance, which is always desirable for a cascode amplifier. But still there is some drawback. The drawback is it consumes relatively large portion of supply voltage, because under one supply voltage you are having more transistors, isn't it? More transistors, four transistors you are using. So it is highly consuming power. Okay, so there is high power consumption here and also heat dissipation. So it is going to be very tedious task while fabricating inside an IC. Okay, so that is one drawback of this particular circuit. Now, to compensate that drawback, again we are going for the second type of mirror circuit. This is a second type of mirror circuit, but the thing is that it is used with BJT, not MOSFET. Okay, so now as of now this MOSFET has been replaced by BJT. So we are going to analyze a circuit using bipolar mirror with base current compensation. So this is again a mirror circuit. What is mirror? Mirror is I0 equal to IRF. Understood? A perfect mirror always produce a output current equal to reference current, which is able to produce in a cascode MOS mirror, what we have learned in the previous circuit. But the complexity with the previous circuit is that four transistors or four MOSFETs are working under a single power supply, that will create more power dissipation, or power utilization will be more. Effective utilization of power will not take place. Okay, low power consumption is not at all possible in that typical MOSFET cascode mirror. For that, we are learning the same thing but with the same mirror circuit only, but with BJT. Okay, so the concept is same. Mirror concept is same. That is, we are trying to achieve current transfer ratio 1:1. That is, from the reference current, we are trying to produce the output current. Okay, reference current will be in some other part of the IC. IC being a complicated, you are having large number of discrete components. Okay, so another discrete component is also utilizing the same current. Means what we have to do? We have to steer the current from IRF to I0. For that, we need to have a current mirror circuit, which is nothing but this. Okay, so this current mirror circuit is known as bipolar mirror circuit with base bias compensation, base current compensation, which is able to produce I naught by I ref equal to 1 is to 1. Okay, I0 by I reference will be equal to 1 is to 1. So see how this is being connected. Here we are using three transistors Q1, Q2 and Q3. Remember that this is BJT and not MOSFET, and I have connected the two emitters together and base also connected. Okay, Q1 and Q2 base I have connected together, and similarly the two emitters are also connected. Now the analysis will be starting from this point. This point. Assume that the two transistors are matched. Assume that the two transistors are matched means their collector current will be same. Understood? Assume that the two transistors are matching transistors means their collector currents will be same. Okay, try to learn from where you have to start, otherwise it is going to be very difficult to write. Okay, so I'm starting from this point. That is, the point is the two transistors are identical transistors means their collector current will be same. So this collector current is equal to this collector current. Okay, so both the currents are same means their base current will be IC by beta. We know what is base current. If the collector current is IC, what will be the base current? Base current is IC divided by beta. Understood? So this is also IC by beta. This is also IC by beta. So normally what will be the emitter current of Q3? What will be the emitter current of Q3? This current, when it reaches at this particular node, it is splitting up into two equal currents, isn't it? Okay, so this current is IC by beta, this is IC by beta. So what is the overall current? The overall current will be 2 IC by beta. Understood? That is what is the emitter current of Q3, which is represented by this equation. So IE3 equal to 2 IC by beta. You know, current that is distinct. KCL, Kirchhoff's current rule, isn't it? So that KCL I have applied at this particular node. Since these two currents are same IC by beta, the entering current to this particular node will be the sum of IC by beta plus IC by beta, which is nothing but 2 IC beta. That is nothing but your IE3. IE3 is the emitter current of Q3. Clear, no? This much very clear. No, any doubts? Now next step is you will find IB3. So as of now, we have finished with IE3. Next thing you will be doing with IB3. IB3 means base current of Q3. You know the equation for transistor currents. IE is equal to IB plus IC. Emitter current is equal to base current plus collector current. So you will put IE3 equal to IB3 plus IC3. And what is IC? IC is beta IB. So instead of IC, you put beta IB3. Common is IB3 you take outside. IB3 I have taken outside. So within the bracket, I have 1 plus beta. Rearrange it and find IB3. So IB3 equal to IE3 by 1 plus beta. And what is IE3? We have already derived the equation for IE3. IE3 is 2 IC by beta. So you can substitute over here. So 2 IC3 by beta divided by 1 plus beta. Why I put 3 here? Because I am writing IB3. I'm writing the equation for third transistor Q3, isn't it? So while writing IE3, you can put 2 IC by 3 because IE3 equal to 2 IC by beta. Okay, so IE3 equal to 2 IC3 by beta you can put here and rearrange. So this will be IB3. That IB3 you can show in the circuit diagram. Okay, so while writing the circuit diagram, don't by heart all these currents because it is very difficult. You can't by heart the circuit diagram and draw. At least you can remember the configuration or the connections, but you can't remember the current values. So current values only if you know the logic to derive, then only you can mark all the current magnitudes in this figure. Okay, so from where should you start? From where should you start? You have to start from this point. Which point? Assume that Q1 and Q2 are matched. From that point only you're going to start this explanation. So assume that Q1 and Q2 are matched means IC is equal to I0 means the base current will be IC by beta. So that will be summed up together to get the emitter current of Q3, which is 2 IC by beta. Once you get this 2 IC by beta by using the current rule, that is current equation I equal to IB plus IC, you can derive the equation for base current, that is 2 IC divided by beta into beta plus 1. Is it clear now? Now at this particular node X, I have written that this node is X. So this node we are going to apply KCL. Okay, at the node X we are going to apply KCL. So here what is the entering current? When you observe the circuit, what is the entering current? entering current is IRF, leaving current is IC, and 2IC by beta into beta plus 1. So these two currents are leaving. IC is the leaving current and another leaving current is 2IC divided by beta into beta plus 1. So according to KCL, the entering current is equal to sum of the leaving current. So IRF is equal to IC plus 2IC divided by beta into beta plus 1. Take IC outside. I hope you have understood this equation how I have written here just by applying KCL at node X. Okay. Take IC outside. Take IC outside. Then take LCM over here. Open the brackets. Open the bracket. You can go to this step. Okay. Open the bracket. So it will become beta square plus beta plus 2 whole divided by beta times of beta plus 1. And find the current transfer ratio. You know what is current transfer ratio? Current transfer ratio is I0 by IRF. Okay. So here instead of IC you will put I0. Instead of IC in the next step you will put I0 because since it is matching transistors always IC is approximately equal to IRF, or else from this equation also you can uh, achieve this particular result. When you consider 2 as a negligible factor, you can neglect this 2. Neglect this 2. So what will happen? This will get cancelled. Why 2 neglect? Because beta is very high. Beta is 100. 100 into beta plus 1, 101. 100 into 101 is a very big value when compared to 2. So you neglect 2. So what happened? Beta into beta plus 1 will get cancelled. So answer is IRF equal to IC. So in the next place, what you will do is, instead of putting IC, you will put I0. Okay. Because IC is I0 only. I'm taking the output from the collector, isn't it? So that IC can now be replaced as I0. And find the ratio. Which ratio? I0 by IRF. So while finding the ratio I0 by IRF, this will go here to the numerator and this will come to the denominator, isn't it? So beta into beta plus 1 divided by beta square plus beta plus 2. You can take beta outside. So beta into beta plus 1 plus 2. Take this outside. So it will be like this. Cancel this. Any doubts? Any doubts with this step? Simple max only. Okay, in the denominator what I have done is I have taken this beta outside. From this beta square plus beta I have taken beta outside, so beta into beta plus 1 plus 2, that is what is done in the denominator side. Then I have taken this outside because I need to cancel with the numerator, so I have taken this outside, and with respect to 2 I have to divide this because while taking the common factor I should divide, isn't it? So 2 divided by beta into beta plus 1, and compared to 1 beta is very high, so 1 can be neglected, so it will be 2 by beta into beta, so 2 by beta square. So this is the equation for current transfer ratio where 2 by beta square is actually the error. Okay, if 2 by beta square is very small, you know that beta is very large, 100, beta square is 100 into 100. Okay, so 2 by 100 into 100 is very much small, so that is very much neglected when compared to 1. So approximately this ratio will be 1:1. Perfectly you can't say that it is 1:1 because of this 2 by beta square error. So 2 by beta square is actually creating the error in current transfer ratio whenever a bipolar mirror is concerned. Okay, this is what actually, this is a bipolar mirror. Why it is bipolar mirror? Because it is using BJTs. Understood? These bipolar mirror, when you compare with the simple bipolar mirror means using only 2 transistors. But here we have used 3 transistors and we have connected in a proper manner like this. In a normal bipolar mirror, you will be having these 2 transistors with IRF. But apart from this, okay, I tell you, in normal simple BJT mirrors or bipolar mirrors, you will have this Q1, Q2 along with this IRF. But additionally, I have inserted Q3. And this Q3 is nothing but the base current compensation. Q3 is offering the base current to Q1 and Q2, isn't it? Q3's emitter is offering the base to Q1 and Q2. That is why its name current mirror with the base current compensation. But when you add this extra transistor Q3, what you are able to achieve is you can achieve a perfect I0 by IRF ratio because this is depending only on 2 by beta square. 2 by beta square is very much small when compared to 2 by beta. Okay, 2 by beta is very large when compared to 2 by beta square. The denominator, when it is large term, means the overall fraction will be very less, isn't it? So here the current transfer ratio is depending upon 2 by beta square, whereas in the simple mirror it is depending on 2 by beta. That is the comparison between the bipolar mirror with the base current compensation and the ordinary simple bipolar mirror. That is not actually in the syllabus. So you just keep it in mind that the simple bipolar mirror is having a current transfer ratio, but it is depending on 2 by beta, whereas a bipolar mirror with base current compensation technique, that is additionally you have inserted Q3, that is able to produce a current transfer ratio that is depending on 2 by beta square instead of 2 by beta. Hence, more perfect matching is, or more perfect 1:1 ratio can be achieved. So this is a better mirror circuit when compared to the simple mirror. And again, it has its own advantage when compared to the first mirror. What is the first mirror that you have learned today's class? What is the first mirror? Before this, you have learned a typical MOS cascode mirror. What is the advantage of the present circuit over this? Here you are having 4 transistors under one power supply. Very difficult. Excessive participation. Okay. But here the 4 transistors have been replaced with 3 BJTs, and it is offering a current transfer ratio of 1:1 approximately, because it is depending upon 2 by beta square only. So approximately you can tell that 1:1 ratio you are maintaining. It is a perfect current mirror. Hence hardware complexity is also reduced. Okay. But the thing is that you are using BJT. Now, what is the problem with BJT then? What is the problem with BJT? BJT means it is depending on beta rather than A0. Okay, so it will not produce a better output or a higher output resistance as we expect from a cascode amplifier. Okay, so always our preference is using MOSFET, because MOSFET is actually less power dissipation circuit, even though you are providing some hardware sacrificing here. That is hardware you have minimized, isn't it? From 4 transistors, you are using only 3 transistors, but you are using BJT. Keep it in mind that you are using BJT rather than MOSFET. BJT is a current control device. MOSFET is a voltage control device, and it will consume less chip area also. It is easy to fabricate also. It is a less power dissipation is very less. Power consumption is very low. Power saving can be done by using MOSFET. Okay, so that and all you have to sacrifice while doing this using this particular mirror circuit using bipolar devices. So Wilson named scientist. So the third configuration. Now I am moving to the third configuration. So in the third configuration, there is a researcher known as Wilson. He tried to fabricate another current mirror circuit again by using this BJT. Again using this BJT, but the thing is that he tried to rearrange that configuration. So whatever the circuit configuration you have learned in the previous diagram, we have made certain alterations. Okay, so not as such we are not drawing, but just we are changing the position of Q3 as shown by Wilson. See, Q3 I have just position, I have shifted to the right side, and it is stacked over Q1. Understood? So this is what is known as Wilson current mirror, or otherwise known as, see, whatever the term I have mentioned here, whatever the term I have mentioned here. See, this is bipolar Wilson. Specifically, it is bipolar because it is using BJT. So whenever you are asked to write about Wilson current mirror, write about BJT, not MOSFET. Okay, otherwise it will be clearly mentioned like Wilson MOS mirror. This is Wilson current mirror. Wilson current mirror means it is equivalent to bipolar mirror, and otherwise it will be clearly stated like Wilson MOS mirror, which will be discussed later. Understood? So as of now, this is Wilson Wilson bipolar mirror. Now I am trying to find out the current transfer ratio of this particular circuit. That is I naught by IRF, whatever we have derived in the previous diagram on the previous version. Same thing I am going to derive for the Wilson current mirror also. So again I'll be starting with this point here. From this point only I'm trying to start. Okay. So try to draw the circuit configuration. Try to remember the circuit connection, but don't try to by heart the equations what I have represented the circuit diagram. It is impossible. Okay. So try with the concept or logic. Then meanwhile you fill. Understood? Hmm? Learn the concept, derive. In between the derivation, you will get some result. Okay. In between that, you go and fill the circuit. Fine. So initially you just draw the circuit diagram, don't label anything. But when in between the derivation, you will get some result about the currents at each and every terminal. Then you can show that results in your circuit diagram. Understood? Any doubts? So here also we'll be starting from here, that is point X. So assume that here the two transistors are matching transistors. So matching transistors means they will be having same current, that is IC. So the collector current of Q2 will be same as that of the collector current of Q1. So it is IC plus IC. Sorry, IC by beta will be the base current. If this is the collector current, IC by beta will be the base current. Similarly, the base current of Q1 is also IC by beta. So the overall current will be 2IC by beta. That is flowing to the node X. Okay. So by simply applying KCL at node X, you will get the overall current, that is 2IC beta, 2IC by beta, that is flowing towards X from Y. Clear now? Now next thing will be writing the equation for IE3. What is IE3? What is IE3? IE3 equal to IB plus IC, isn't it? What is IB? IB is IC by beta, that is 2IC by beta. How did you get 2IC by beta? Because 2IC by beta is the overall current entering here. Okay, so this we can, I think this we can deal later. So as of now, you just remember this 2IC by beta. So 2IC by beta is the overall current that is entering to X. Now you concentrate in this term Y. Concentrate in the term Y. In that Yth position, or Yth node, IC is the leaving current. Again, 2IC by beta is the entering current, isn't it? IC is the leaving current, 2IC by beta is the entering current. Sorry, leaving current. So what about the entering current in Y? Entering current is equal to sum of the leaving current, isn't it? So the entering current in Y will be the sum of this current and this current. Understood? The sum of 2IC by beta and IC. So these two currents will added up together to get the total entering current in Y. So that is what is shown here in equation number 1. So the total entering current in Y to the node Y can be written as IE3 because that is emitter of Q3, isn't it? This is emitter of Q3. So this current can be written as IE3, which is equal to 2IC by beta plus IC. That is this current plus this current. Okay, 2IC by beta plus IC. Take IC outside, so 1 plus 2 by beta. This is the overall current that is entering to Y. Clear now? Now, based upon this, you will be writing the current equation for Q3. And based upon that, I will be writing equation for base current. Okay, you know that IE equal to IB plus IC. So IE3 equal to IB3 plus IC3. What is IC3? Beta IB3. Take beta outside, IB outside. So 1 plus beta IB3. Okay. And from this find IC. Sorry, IB. IB is IC into 1 plus 2 by beta by 1 plus beta. I repeat. Once you get the emitter current of Q3, just write the equation of a transistor. Current equation of a transistor is IE equal to IB plus IC. IC is beta IB. So from that you can just simply write the equation for IB. Sorry, IC. Understood? So this is the equation for IC that you have derived, and I have shown the same equation over here. Understood? Any doubts? See, what I have done is IE3 equal to IB3 plus IC3. IC3 is beta IB3. Take IB3 outside. IE3 already we know what is IE3. We have derived it. IC into 1 plus 2 by beta. Equate this. This and this I equated. And I found the equation for IB3. Once I get the equation for IB3, simply multiply by beta, you will get IC3. Okay. So as of now, you get IB3 and you got IC3 also. How did you got? By writing the equation IE3 equal to IB3 plus IC3. Substitute for IE3. Okay. And solve for IB3 in terms of IC. So once you get IB3 in terms of IC, simply you can write IC3 also by simply multiplying by beta. So this is the collector current of third transistor. What is this IC3 actually? IC3 is the output current, that is I0. IC3 is your Q3, isn't it? IC3 is a collector of Q3, which is the actual output current. So instead of putting IC3, now you can put I0. So this is the equation for I0. Equation number 4. Understood? And you are trying to derive the current transfer ratio of I0 by IRF. As of now, you got I0. Now we are focusing on IRF. Okay. We are trying to find the current transfer ratio of I0 by IRF. Till equation number 4, we have derived the equation for I0. Now we are trying to develop an equation for IRF. For that, apply KCL to node Z. So come to this node. So initially we have developed an equation for Y. Then we have solved the equation for IC3 and IB3, and from which we have derived an equation for I0, because IC3 is nothing but your I0. Okay. Now apply KCL at Z. So at the node Z, IRF is your entering current. This is your leaving current. Already this current we have solved, isn't it? This current is IB3, which you have solved. This is IC. So IRF is equal to, this is entering current, these two are leaving current. So IRF equal to IC plus IB3. So IRF is equal to IC plus this is IB3. IB3 we have already solved this thing. Okay. Take IC outside. So this is IRF. So by observing equation number 4 and 5, we have developed equation I0 and IRF in terms of IC. Now divide these two. IC will get cancelled. IC will get cancelled. In the denominator side, you can take LCM and simplify so that 1 plus beta will get cancelled. Here also take LCM. In the numerator portion also, here take LCM here. So beta plus 2 whole divided by beta. That denominator beta and this beta will get cancelled. Again, this 1 plus beta and this 1 plus beta will get cancelled. So it will be like this. Okay. This will be the equation. Now I need to cancel the numerator. For that, similar to what we have done in the previous case, that is the bipolar base compensation technique. There also we have taken beta plus 1 outside. Here beta plus 2 is common. So take it outside. So it will be 1 here plus 2 divided by beta into beta plus 2. Cancel this. Assume that 2 is very small. So beta into beta, beta square. Any difference? Same, no? So what is the arrangement or the modification that Wilson had did? Wilson had used the 3 transistors Q1, Q2, Q3. Same 3 BJTs. But he just changed that position of Q3. That is Wilson's configuration. Okay. And he was able to derive this current transfer ratio, which is very much likely 1:1. Very much close to 1:1, because 2 by beta square can be neglected, isn't it? Beta is very small, very large. Beta square is still large. Therefore, 2 by beta square is very small, which can be neglected when compared to 1. So the ratio will be 1:1. So he is able to achieve a perfect current mirror circuit here also by using this BJT. But the problem is that again it is BJT. So what he tried to do is, he will try to find out this output resistance of this transistor, this configuration, that we will learn in the next class, don't worry. Okay. And he will prove that this output resistance is not desirable for our case. That is, our case is cascode amplifier case. Understood? For that, he will modify the same circuit with MOSFET. That is Wilson MOS mirror. Understood? Understood why he has gone for Wilson MOS mirror rather than Wilson's BJT mirror? Because in the Wilson's bipolar mirror, the output resistance is only beta R0 by 2, which is not suitable for us. Means for cascode amplifier. All these we are using for cascode amplification, isn't it? All the mirror circuit we are discussing, we are trying to incorporate with our amplifier. Amplifier need another resistance. Which resistance he need? He need the resistance of this value, that is GM3 R3 into R0. That is not able to achieve with your Wilson's bipolar mirror. Understood? So Wilson what he did is, he tried to form a new mirror which is known as Wilson MOS mirror, where he replaced this BJT with MOSFET. The difference is that same current transfer ratio 1:1 he can maintain as he had maintained in Wilson current mirror. Also simultaneously he is able to achieve a output resistance which is as desirable for a current cascode amplifier. Okay. But the drawback of this Wilson current mirror is that, what is the Wilson current mirror? Current mirror means it is with using bipolar BJT. This thing is that though it is offering approximately 1:1 ratio, it is offering 1:1 ratio, but the thing is that it is not able to produce a desirable output resistance that we will learn in the next class. Okay, and to compensate with that output, or to find a solution for that output resistance, he replaced this BJT in the same circuit, no modification. He replaced that BJT over the MOSFET, same circuit. So it is known as Wilson MOS mirror. Okay, Wilson current mirror, it is bipolar. Wilson MOS mirror is, it is based upon MOSFET. Understood? So these we'll discuss tomorrow. Any doubts? Any doubts? Can I wind up then? Okay. Thank you all.
Game show na game ಅದೇ ಏನೇನೋ